All right, welcome back to Online Calculus 2. In this video, we're going to cover our introduction to sequences leading up to introducing infinite series. All right, so let's kind of properly introduce what sequences are, but more importantly, infinite series. Now, there's a number of ways we could do this, but I like to start with something known in philosophy called Zeno's Paradox. Now, Zeno's Paradox is the seemingly simple problem of walking 2 units, 2 feet, 2 meters, 2 miles, whatever. The units don't matter here. We're just trying to walk a finite distance. All right, we can do that, no problem. So there seems to be no paradox. The paradox arises if we try to split this total journey by walking to each halfway point at each step. Now, if we start at the left and walk to the first halfway point, we've walked the total distance of 1 unit. Now that we're at the halfway point, we have to walk to the new halfway point, walking an additional 1/2 units. Where we currently are, we have to walk to the new halfway point, walking an additional 1/4 of a unit. And you can see what's happening here. No matter how much distance is left to walk, there's always half of that, no matter how small that distance is. The next amount you would walk is 1/8. And as we continue that forever, we're always walking some distance. Even a very, very, very small number can be split in half. All right, and this is where the paradox arises. If we split this journey into an infinite amount of steps, walking to the halfway point, it seems as if we're never going to reach the end. Now, we know we can walk 2 units. We do that every day. So how do we resolve this paradox? Well, the ancient Greeks didn't know about calculus and limits. Now, what we have here is our first infinite series. And we're going to say an infinite series is basically just a sum or an addition of an infinite amount of numbers. So from what we found in Zeno's paradox, we had 1 plus 1/2 plus 1/4 plus 1/8. The next amount would be 1/16. And if we add all those up forever, that should be the total distance we cover, splitting our journey into an infinite number of steps. Now, by looking at it this way, we're left with a kind of a problem. We know how to add up a finite amount of numbers. I don't care if it's a list of 10 numbers or a list of 1 million numbers. You can still add up any finite amount of numbers. Add them in pairs and then keep adding from there on. What we have to address is a new conceptual question. How do we add up an infinite amount of numbers? If we were to try to sit there and just add each number in the infinite series, we would never reach the end. There would never be a point at which we can say we're done adding and then hit equals on our calculator, for instance. Now, before we move on to kind of the rest of the course, the other topics related to sequences and infinite series, we could give an intuitive answer to what the infinite series from Zeno's paradox should add up to. Now, all those numbers, 1, 1/2, 1/4, 1/8, were the individual distances we walked. And remember, we're trying to walk a total distance of 2 units. Now, whatever we introduce as a way to add up an infinite amount of numbers, we better find that it's consistent here, giving us that this infinite series from Zeno's paradox has a sum of 2. All right, let's take a look at some other examples of infinite series. So there's just a few of them there to kind of get motivated for the rest of the course, why we might want some kind of results on how to deal with infinite series. The first one listed there is what we found from Zeno's paradox. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, so on and so on. All right, a second example there is, let's say we just add up not the natural or counting numbers, but their reciprocals. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 forever, ad infinitum, if we want to get fancy. All right, the third one there is one of my personal favorites. We're going to add up the reciprocal squares of the natural numbers. 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared, so on and so on. One last one there is what you might have kind of thought of in elementary school. At some point, you were maybe thinking, what is the biggest number? And then you learn there is no biggest number. In a similar fashion, we might think, well, if all my counting numbers, 1, 2, 3, 4, and 5, what if I were to add all them up? So what's 1 plus 2 plus 3 plus 4 plus 5 forever? Now, two of these we're going to define to have a sum. This is what we'll be getting to in kind of some later topics for the course. The first one has a sum of 2. That's from Xenos Paradox. The third one there has a sum of pi squared over 6. Now, that's not going to be accessible for quite a while, but those are two known results. We're going to define these two infinite series, the first and third, to be what we'll call a convergent infinite series. Now, the second one there, 1 plus a half plus a third plus a quarter, is, I'll say, a little more complicated. So we'll wait to introduce that. That's going to be something we call the harmonic series. But the last one down there, 1 plus 2 plus 3 plus 4 plus 5, forever, we should be able to give a basic answer. Notice each of those numbers we're adding is getting bigger. So we should be able to say, in some sense, that the sum is infinite. If we were to add up all the counting numbers, we should get infinity. Now, that is one possible answer. What we're going to learn kind of later in the calc sequence, some of you maybe or won't get to that, but there's an alternate answer. 1 plus 2 plus 3 plus 4 plus 5 forever does mathematically also equal -1/12. And that is highly counterintuitive. And that's part of the problem when dealing with infinities, infinite processes. Our intuition can break down when dealing with infinities. So we're going to need some mathematical tools to deal with that, and we'll take a look at that and what comes next.